Hello everyone, this is Professor Roman. Welcome to the 27th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to talk about distributing balls into boxes. Combinatorial problems can generally be phrased in a variety of different ways, and one of the more common ways to phrase problems is in terms of placing balls into boxes. It strips the problem of irrelevant, although important from a practical point of view, but irrelevant from a mathematical point of view, issues, and just focuses on the mathematics. So it's important that we spend some time discussing this model, this language. Now, there are several possibilities for the distribution of balls into boxes. The balls can be either distinguishable or indistinguishable. These are issues we faced in the past. Boxes can be either distinguishable or indistinguishable. The distribution can be done with exclusion, which means that you can have at most one ball in each box, or without exclusion. So that allows any number of balls to be in a given box. And it can also be required that every box receive at least one ball. In this chapter of the book, we're going to confine our attention to distinguishable boxes, and I'll distinguish them somehow, usually by a label 1 through n. The case of indistinguishable boxes is a lot more complicated, so we're going to postpone that discussion till later on. As a matter of fact, the case of distinguishable boxes is really just another way to view words over an alphabet and multisets. So the mathematics here is going to look very familiar. But as I said, the language is important to have some feeling for. So this table is a reference. It lists the cases we're going to discuss and actually the number of ways to do each type of distribution and a reference to the theorem that's relevant. And if you glance over this arithmetic here, you'll see that most of this is stuff we've seen before. Here are the two multi-set coefficients that we've seen before. And when we're placing distinguishable balls into distinguishable boxes, I'll probably also number those so we know how to distinguish them. When the balls are not distinguishable, then all that matters is the number of balls that fall into each box. In other words, the multiplicity of each box, where a ball chooses a box, two balls in the same box choose that box twice, the box has multiplicity 2, and so on. So let's take the case first where the balls are indistinguishable. We have k balls that are indistinguishable. And so again, all that matters is the number m sub I, which will be non-negative, of balls that fall into box I. And I ranges from 1 to n if there are n boxes. And, of course, the sum of these multiplicities have to add up to k, which is the number of balls. The only other issue here is the boundary conditions that may be placed on the multiplicities m1 through mn. So, first case, distributing k distinguishable balls into n distinguishable boxes with exclusion. So that means each box can receive at most one ball. Well, then what you are doing when you place a ball into a box is you are choosing that box. So the number of ways to make this form of distribution will be n choose k. The choices are made by the balls. If we add that no box can be empty, that's not going to be possible. You have both exclusion, which means each box gets at most one ball, and you have no box empty, which means each box gets at least one ball. In other words, every box gets a single ball. There's only one way to do that, provided that k is equal to n. You have to have the same number of balls as boxes. Otherwise, there's no way to do it. As to the distribution being done without exclusion, we still have this multiplicity equation. Okay. And now the bounds on the multiplicities are just the natural bounds. And so this is the multiset coefficient, n multi-choose k. Every time you drop a ball into a box, you're choosing that box. Without exclusion and no box empty just calls for the lower boundary translation we used before. Here's our multiplicity equation, and here is the lower bounds on the multiplicities. We do a lower bound translation, and we get this multiset coefficient. So this is all pretty straightforward because we've discussed most of this before. Okay, let's take a look now at when the balls are distinguishable. So here it is much more than just the matter of the number of balls in each box, because the balls are distinguishable. So each ball drop into a box represents a choice of the box, as it did before. In other words, a choice of a box number, 1 through n. And so the complete choice can be described by a word of length k. The first letter in the word is where is the choice made by the first ball number 1. Okay. The second letter in the, or number in this case, integer, in the word represents or is the box number that is chosen by ball number 2, and so on. So this word seems reasonable to call it a choice word. I just made that up. I don't know if anybody else does use this phrase or not. Okay. So it then boils down to the issue of multiplicities. Okay. So with exclusion, that means at most one ball per box, which means the box numbers that are chosen by the k balls are distinct. And so this is a word of length k over a set of size n, no duplicates. In other words, it's a permutation of size k over a set of size n, so this is the number of ways of doing that. If we add no box is empty, then the word will have length n, must have length n, so k has to equal n, and it's a permutation of the set of box numbers, and there are n of those, so it's n factorial. 0 if k and n are distinct. Without exclusion means that the words that are formed, the choice word, can have repetitions, okay, with unrestricted numbers of repetitions. And so this is a case for the fundamental counting principle, the multiplication rule. There are n choices the first ball can make, n choices the second ball can make, and so on. So it's n to the k. without exclusion and no box empty. This is more involved. It's a little bit surprising. You might think that all the cases so far have been quite simple. This one is much more complicated. Okay. So unlike the case of indistinguishable balls, when the balls are distinguishable, it's not so easy. You can't do lower bound translation. That doesn't work. So we can't remove the no box empty condition just by subtracting a number from the multiplicity equation. So that's a hint that something more involved is going on. And in fact, we don't have yet the mathematical machinery to produce a formula. This is what the formula looks like, and so it sort of makes it clear that something more is going on here. Okay, I mentioned some time ago that I think I put it in one of the tables of progress. There's no simple formula in this case. That's the formula. I wouldn't call that a simple formula. I mean, it could be worse. I mean, at least it has a nice pattern to it. But we're going to have to postpone the derivation of this formula until we have more machinery. But we can summarize what we've done so far. I put it into two separate theorems. This for distinguishable boxes. We've already discussed all of this, and this is for the distinguishable boxes, no box empty. Okay, so these are the formulas. So that's it for distinguishable boxes. It's not too bad. Most of it is a reworking of what we've done before in a different language, with the one exception of this formula, which we'll discuss later. Okay, thanks for watching the video, and I hope to see you in the next video, where we will talk about, we'll go on to the next chapter, talk about the principle of inclusion and exclusion, which is precisely what we need in order to deal with this formula.